Hey everyone, welcome back to Linear Algebra. This will be lecture 8 of the course, and in this section we're going to discuss inverses of matrices. Okay, so let's go ahead and jump into that. So this will be section 2.4, we'll call it 2.4, and inverses of matrices is the topic. Okay, so in this section, we're going to consider whether a given n by n matrix A has what really is a multiplicative inverse. Okay, so given A, an n by n matrix, right? It's going to be a square matrix. Question is, does A have a multiplicative inverse, right? And so in particular, what we're interested in, what we're looking for, so we're looking for an A inverse matrix such that A times A inverse is equal to A inverse times A, which is equal to the identity matrix, the n by n identity matrix. Okay, so think about so this course, you may or may not have had an abstract algebra course. You may or may not know what a multiplicative inverse is. The basic idea behind a multiplicative inverse is it's some number that, when multiplied by, equals 1, right? So for example, 10 has a multiplicative inverse of 1 over 10, right? And that's because the product there is equal to 1. Okay, so any real number will have some kind of a multiplicative inverse. If I have 0.576, the multiplicative inverse is 1 over 0.576. I multiply those together, I get 1. So this is it's very similar to this concept. Maybe it even is identical to this concept. We have to think that through. But basically, we're looking for a matrix that the product of the matrix with its inverse is equal to the identity matrix. So in linear algebra, we tend to think of these identity matrices as filling the role or fitting the role of the unit, right? Sort of like the 1 in the real number system. These identity matrices are like the unit. Okay, and so that's kind of the motivation. And so let's go ahead and talk through this in more detail here. So let's go ahead and define it formally, which we sort of already have, but let's do it with some, a little more formal. So let A be an n by n matrix. Okay, let A be an n by n matrix. Then B is the inverse of A if and only if B times A equals A times B equals the identity, the n by n identity matrix. So that's kind of the definition here. Now, we typically will use the notation we introduced above to denote the inverse, this A with a -1 exponent, but we haven't quite filled in all the gaps to where that would be appropriate yet. So we'll talk about something in a moment that will make that more formally appropriate. Now, it's important to notice that if B is an inverse of A, then naturally there is a reciprocity there. A is going to be the inverse of B. All right, so just something to note. If A is the, well, I think we'll do it this way. If B is the inverse of A, then A is the inverse of B, right? So just kind of note the reciprocal, the reciprocity, right? So if one is the inverse of the other, then the other must be the inverse of the first, right? So an example. Let's do an example here. And I'll leave it to you to verify this, but if we have A equals 1, -4, 1, 1, 1, -2, and -1, 1, 1. So this 3 by 3 matrix. And if we have B equal to 3, 5, 7, 1, 2, 3, and 2, 3, 5, then A and B are inverses of one another. B is the inverse of A is the inverse of B, right? So we'll have, and you can confirm this multiplication, please do. Please do confirm this. You know that basically if you take these two matrices and you multiply them together, you do indeed get the identity matrix, the 3 by 3 identity matrix. Okay, and also notice that the order in this example doesn't matter because of the inverse, right? So A times B is the identity, B times A is the identity, and so B is A's identity and A is B's identity. Okay, so A and B are inverses of one another. Okay. Now, not every matrix, not every square matrix has an inverse. Most do, but not everyone. Okay, here's an example of a matrix that does not have an inverse. So the matrix A equals 2, 1, 6, 3 has no inverse. Okay. Now, one way you can kind of see this is let's pretend that there is an inverse, and let's pretend it's A, B, C, D. Okay, we don't know what those numbers are, but let's just assume for a moment that A does have an inverse. Then what can we see? Well, if I take A times A inverse, right, if I multiply these together, 2, 1, 6, 3 times A, B, C, D must equal 1, 0, 0, 1, right? That's the definition. Okay. Now, what does that mean? Well, I can do the multiplication here. So 2 times A plus 1 times C. So I get 2A plus C. And then 6 times A plus 3 times C. And then 2 times B plus 1 times D. And then 6B plus 3D. And that's equal to 1, 0, 0, 1. Okay. Now, when you look at this, it may or may not be obvious what the problem is, but let's draw it out here. Like, consider this: 2A plus C equals 1. Okay, so notice that 2A plus C equals 1. And also notice that 6A plus 3C equals 0. Okay. But, I mean, this is obviously not possible, right? There's no such A and C, right? This is contradictory. Now, do we see why it's contradictory? Can anybody see why this is contradictory? Well, I mean, this is a scalar multiple, right? If I take 3 times 2A plus C, I get 6A plus 3C, right? These are this guy here and this guy here. This is just 2 times or 3 times this, right? So there's no A and C that's going to make this 1 and this 0 simultaneously, right? We can see it easily because the one is a scalar of the other. So therefore, there is no such A, C, right? Right, and you could probably identify something similar if you look at the B's and the D's, right? But basically, you can just kind of look at this and see that, well, no such A and C is going to exist. And indeed, if you try to solve this system, you will find that it's an inconsistent system. Okay, you can think of this as a system with a 2 by 2 coefficient matrix, just 2, 1, 6, 3. Try to solve that system, and you'll find that you can't. Okay, so not every matrix has an inverse. And this is an example of one. Okay, let's take a look at a theorem. Let's let A and B be n by n matrices. Okay. Then if either of A, B, or BA is equal to the identity, then the other product is as well. Right, so this is when we first introduced the definition of what a matrix is, you may have thought to yourself, so when we first said A times B equals B times A equals the identity, you may have thought to yourself, well, what if just A times B equals the identity, but not B times A? You may have thought to yourself this question, which would be a very pertinent question. So what if just one ordering produces the identity, but the other ordering does not? Would B still be the inverse of A if just one of them is true but not the other one? Well, this theorem is directly addressing that. It's saying, look, if either of them is equal to the identity, then the other must be. Okay, the other must be. Okay, and this is a relatively easy proof, I think. And I think I'm going to leave it to you guys to prove it. Okay, so there's a couple of ways to do it. I think you can do it by direct proof. You could also do it by contradiction. So there's a couple of different ways to try it. Okay. But it is in fact true that if AB equals the identity, then automatically BA must equal the identity as well. Right, so this addresses this kind of nagging concern that comes up when you first see the definition of an inverse. Okay. All right. Terminology. So we say a square matrix is singular if and only if it does not have an inverse. Okay, so if a matrix does not have an inverse, we call that matrix singular, a singular matrix. And then, obviously, if a square matrix does have an inverse, it is called non-singular. Okay, so it's non-singular. Most matrices are non-singular. There are examples of matrices, however, that are singular. We just saw one, right? So our previous example, A equal to 2, 1, 6, 3, is a singular matrix, right? Because it does not have an inverse. It does not have an inverse. All right. Now the next item here is it's going to address another question that maybe comes up when being introduced to the idea of an inverse, and that is the uniqueness of the inverse. Okay. Okay, so if B and C are both inverses of an n by n matrix A, then B equals C. Okay, so this is the idea that there is a unique, one and only one inverse for A. A has only one inverse. It doesn't have a distinct range, a variety of inverses, just one. Just one. Okay, and this proof is really easy, and so we'll go through this one quickly. All right, and this is just a simple, you can derive this really quickly. So take B, we'll start with B. And, well, so we're going to assume that B and C are both inverses of a matrix A, right? That's our assumption. All right, so we'll start with B, and we know that B is equal to B times the identity matrix. Okay, no problem. That's just like multiplying by 1, so we know that's fine. And the identity matrix would be equal to A times C, right? Because C is assumed to be an inverse of A, right? So A times C is equal to the identity, so the identity is equal to A times C. And we know that matrix multiplication is associative, right? We've seen that from earlier in the course. So B times A times C, right? You can kind of change the order of the multiplication. Not the order, but you can associate them differently, right? So I can multiply B and A first and then multiply by C. Note, I'm not changing the order, I'm just changing the, I'm just reassociating. Okay, now B is also an inverse of A, right? So B is also an inverse of A, so that means this is equal to the identity matrix times C. And of course, the identity matrix times C is just equal to C, right? And so you can see that indeed these are the same. They must be the same, right? This is a nice simple, this is the kind of proofs you like, right? They just, it's, you know, start with one thing and just derive directly the other, right? So perfect, exactly what we wanted to see. So B equals C if they're both inverses of a matrix A. And so given the fact that the matrix inverse is unique, we will typically denote the matrix using the inverse notation. So because the inverse is unique, we will typically denote the inverse of A using A inverse like that. Much more convenient notation. Okay. And that's you know what we started off with, but then we first needed to know that the inverse was unique before we could probably safely use this notation. Right, so here we go now, we're good. Okay. So given the inverse, given what the inverse is all about, we can now move on to some other things that use it heavily, right? And so one of those things is the definition of negative powers of a matrix. So let A be a non-singular matrix, n by n, okay? Then the negative powers of A, all right, the negative powers of A are given as, okay, so A inverse, right? So the, you know, it's kind of starting with this one. A inverse, this is the unique inverse of A. This is the unique inverse of A. Okay. Then, you know, for k greater than or equal to 2, right? So for every other, all the negative integers, you have A to the negative k is just equal to A to the negative 1 power raised to the k power. Okay. So this is a very natural definition. I hope you can see how and appreciate how natural this is, right? If I think of like, let's think about how nicely this jives with kind of the things we're used to with like rational numbers, for example. So if I have 5, right, then 5 to the negative 1 power is 1/5, right? And this is the inverse of 5, right? These are inverses. So that's the first arrow. That's this one. What if I have 5 to the negative 4th power? Well, that is 1/5 to the 4th power, isn't it? Right? So you can kind of think of this as 5 to the negative 1 to the 4th, right? And that's literally the same thing as item 2. Right, so this is hopefully an extremely, like, you can just kind of recall your intuition about rational numbers when you're thinking about negative exponents on matrices. It works the same way. Of course, the multiplication is totally different, and how you interpret it is different, but this is the basic setup, and it's very similar. Very similar. All right. Excellent. Excellent. A quick example of that. Let's just make sure this is crystal clear. So let's refer to the A from the previous examples. 1, -4, 1, 1, 1, 2, and then -1, 1, 1. And A inverse we saw was 3, 5, 7, 1, 2, 3, and 2, 3, 5. Okay. So if I'm interested in A to the negative third power, then I know that this is basically A inverse cubed, right? And so another way to think about that is it's the inverse here, 3, 5, 7, 1, 2, 3, 2, 3, 5 cubed, right? This is a notation we haven't used yet, but technically I'm just taking this indicates that I'm going to multiply the matrix by itself, right, 3 times, right? And so it's 3, 5, 7, 1, 2, 3, 2, 3, 5 times 3, 5, 7, 1, 2, 3, 2, 3, 5 times 3, 5, 7, 1, 2, 3, 2, 3, 5, right? So that's what we mean by A to the negative third power. It's really the inverse cubed. Okay. And again, I'll leave it to you to figure out what this product actually is worth, what it equals. Okay. All right. Very good. Very good. How about a nice theorem? Let's let A and B be non-singular n by n matrices. Okay. Then A inverse is non-singular. Well, this is obvious, right? We knew this from the start, right? This is just a reciprocity, right? If A inverse is the inverse of A, then A is the inverse of A inverse, right? But this is a nice. We like to go through this because A inverse is non-singular, and this introduces like some notational conventions. If I take the inverse of the inverse, I get back to the original. Right? This is just literally applying the definition: A times B equals B times A equals identity, right? And so if A inverse is the inverse of A, then A inverse is the inverse of A inverse, right? So basically you can kind of think of it, when you take the inverse of an inverse, you get just A back. And this is great notation as well, because -1 times -1, the way you would normally want to treat these powers, when you multiply those together, you just get A times 1, A to the 1 power, right? Which is just A. So that's that. A to the, so remember, A is non-singular, then any power of A, any positive power of A is, any integer power of A is non-singular as well. And we could say A to the K inverse is equal to A inverse to the K power, which is equal to A to the negative K. That's great. Again, nice notation, right? If I want to know the inverse of A to the K, then I can just kind of do this, right? I can use the normal to just think of this as the matrix, identify the inverse with this notation. I know I can flip those, and so I know that I can also multiply them together and get negative K, right? Which is the way you'd want to notate that. Perfect. If two matrices are non-singular, then their product is non-singular as well. So if I multiply A and B together, that is a non-singular matrix. So it's non-singular, and AB inverse is equal to B inverse A inverse. Okay, so if I have A and B, and I know they're non-singular, and I know their inverses, then I know the inverse of their product, right? And A times B, the inverse of that is actually B inverse A inverse, right? So the order reverses when we multiply together the inverses, the inverse matrices. So that's kind of an interesting and maybe possibly unexpected result. Okay, and then finally the last one, the transpose of A is non-singular as well. And you may be able to guess, but if I take the transpose of A and I identify the inverse, that is going to be equal to the inverse of A transposed. Okay, so that is this is a great theorem. Lots of useful little items here that we'll use over and over. Right, just dealing with exponents and inverses. Let's prove these two. So we'll start with 3. So what do we wish to show? We wish to show that AB inverse is B inverse A inverse. Okay. Well, what we're going to do is we're going to start with AB, and we're going to multiply it by B inverse A inverse and see what happens. See if it satisfies the definition of an inverse. Okay, and so just multiply those two together. Well, just using associativity here, we have A times B, B inverse times A inverse, right? And that's equal to A times the identity times A inverse, which is of course A times A inverse, which is of course the identity. Okay, so given AB, then AB's inverse is equal to B inverse A inverse. We can see that here. Right, and now one thing that we also should maybe look at is the order, right? So we should be able to confirm that B inverse A inverse multiplied on the other side against AB would produce the same results. Exact same argument. I'll let you guys go through that on your own though. Works exactly the same way. You can kind of see from the way it's structured that the middle two matrices are going to resolve down to the identity, and then be left with the outer two, which is also the identity, right? So you'll get there easily. All right, so that's the proof of 3. Let's take a look at a proof of item 4. Now for 4, what are we trying to show? We wish to show that A transpose inverse is equal to A inverse transpose. Okay, so let's start with the transpose of A, and let's multiply it by this and see if it works. Okay, so let's multiply it by that. So A inverse transpose. Okay, now we saw a theorem a while ago that said if we have two matrices and we transpose, and both of them are transposed, then we could multiply the originals together and kind of reorganize this a little bit. Let me remind you. So recall, right, if I have AB transpose, then that's equal to B transpose A transpose, right? Remember that? So this was from a previous theorem. Okay, we're going to use that here. We've got A transpose and we've got A inverse transpose. So that's going to be equal to A inverse A transpose. We're going to reverse the order here. So A is first and then it's A inverse. And so we reverse the order, it becomes A inverse A. Okay, and we can clearly see that this is going to be the identity matrix transposed, which is just the identity matrix. Okay. Perfect. That's exactly what we want. And the order doesn't matter here, right? You can flip the order the other direction as well, and you'll get the same thing. Okay, so namely A inverse transpose times A transpose. Well, that's just A inverse transpose, which is the identity matrix, transpose, which is the identity matrix. So that one works. Okay, very good. Very good, very good. We'd previously seen, we previously had a theorem about exponents on matrices where we were able to look only at positive integer exponents. Well, now we can extend that theorem to all integers, right? So here's the theorem. If A is a non-singular matrix and S and T are any integers, then two things. First, A to the S plus T power is equal to A to the S times A to the T. And secondly, A to the S to the T is equal to A to the S times T, which is equal to A to the T to the S. So the usual types of things that we want to be able to do with exponents, we can now do. Previously, when we looked at this theorem, it was for positive integers only. But now we know how to deal with, in particular over here, we know how to deal with negative integers, right? We know that it's, when we're talking about a negative exponent, we're really talking about an inverse raised to a positive exponent, so we know how to interpret those now. Okay. All right. Excellent. So these are kind of like, this kind of wraps up, I mean, this will sort of wrap up maybe the discussion of properties of inverses. I mean, we'll see more also as time goes on, but now I want to kind of shift the conversation or shift the focus a little more towards how do we find the inverse of a matrix. So how do we find the inverse of A? Okay, so we've kind of talked about what the inverse is, some of the properties. Now, how do we find them? Okay, we're going to start with kind of a special case, and that's the case of a 2 by 2 matrix. Okay, so let's start with a 2 by 2 matrix. The 2 by 2 matrix is unique with regards to identification of the inverse because there's actually a really quick and easy way to do it. You can tell very quickly whether a 2 by 2 matrix has an inverse and identify that inverse really quickly. This isn't necessarily true of matrices of dimensions higher than 2 by 2. So let's talk through the theorem and we'll prove it, and then let's do an example. Okay, so the matrix, and we'll say the matrix is equal to A, B, C, D, 2 by 2 matrix. has an inverse. It has an inverse if and only if, and we're going to call this delta, and it's going to be equal to A times D minus B times C. Okay, so A times D minus B times C. So the matrix A has an inverse if and only if this delta number is non-zero. Okay, so the matrix A has an inverse if and only if this AD minus BC is not equal to 0. Okay, in such cases, right, when an inverse does exist, when we do have a non-zero delta, in such cases the inverse can be identified as, well, let's write it out, ABCD, the inverse, it'll be equal to 1 over delta times dA negative B negative C. Okay, so what have we done here? Well, first of all, given a matrix, we can check to see whether it's singular or non-singular very quickly. Multiply two numbers together, subtract another product from it. So A times D minus B times C. It's like the cross, multiplying on the diagonals. If that number is non-zero, then this matrix definitely has an inverse. And when it has an inverse, you can find the inverse by simply switching the location of A and D. So D comes up to A's position, A goes down to D's position, and then making the other diagonal variables negative, or flipping the sign, right? So if they're positive here, you make them negative. If they're negative here, you make them positive. So flipping the sign. And that becomes the inverse. Okay, we'll prove this in a sec. Let's do an example just to make sure we're clear on this. How about this one? M equals -5 to 9 -4. Okay, so delta should be equal to A times D, so that's -5 times -4 minus, and then it's B times C, so 9 times 2. So what I have there, 20 minus 18, so 2. Okay, so that's non-zero. So an inverse exists. So the M inverse exists, and M inverse equals 1 over delta times, I'm going to write it out first, dA negative B negative C, which in our case is 1/2, 1 over 2, delta's 2, and then we'll switch the order here, so it'll be -4, -5, and then instead of 2, it's -2, instead of 9, it's -9. Okay, so this is the inverse, and we can kind of divide these down. In this case, we get -2, -1, -9/2, and -5/2 for our inverse. Okay, and so there's the inverse of M, and you can confirm this. You should confirm this. Try to multiply M by M inverse and make sure that you get an identity matrix, a 2x2 identity matrix. Okay, so let's prove this theorem. Let's prove this. Let's walk through how this works. Okay. Proof. So let's assume, first of all, that the inverse exists. Okay, so assume A inverse exists. Okay. Then let's consider our delta. Delta equals AD minus BC. Okay, let's multiply some things together here. So if I have my ABCD matrix, there's my A. I'm going to multiply it by DA negative B negative C, right? So D negative B negative C A. This is an A. And the reason I'm doing this is because when I multiply this together, I get A times D minus B times C. And then I get negative BC plus DA. Right. So, well, okay, let me do it. Sorry, this upper one. Let's do this in the right order. So AD minus BC, and then CD minus CD. Right. So I get a 0 down here. And then up here I get negative AB plus AB. So I get a 0 up here. And then this bottom section I get negative CB plus AD. Right? And so that's just a little out of order, so let's rewrite it in the order, and you'll see that I get this. Okay, when I multiply those together. And so notice this is just delta, right? So I get delta, 0, 0, delta. Okay, and I can think of that as just delta times 1, 0, 0, 1, right? Okay, and so that's just delta times the identity matrix, I2, I guess, not IN. Okay, and so clearly, if the identity is going to exist, it has to be 1 over delta, right? Because I want this product, the matrix A times its identity, to equal just I, right? So this implies that I need to do this instead: AB CD times 1 over delta times D negative B negative C A. Right, and the reason is because, you know, when I go through this exercise, I multiply, you know, so maybe you'd want to pull the delta out front. Oh man, negative B negative C A, right, when I do that. Right, well, this part here is what we just calculated, isn't it? We know that that's just this, and then it's this, and it's this, and it's that. So I have 1 over delta times delta times the identity, which is just the identity. Right? So the inverse has got to be equal to 1 over delta times D A negative B negative C. Okay? And so that shows you that if the identity exists, it's going to have this form. It'll have to have this form, won't it? We know that also that the identity is unique, so there isn't some other way to convert these numbers to get to the identity. Right? This is the only way. Okay. Now the other direction, let's assume next that the delta is 0. Well, what's going to happen then? Well, it's kind of the same thing, right? A, B, C, D times D negative B negative C A is going to be equal to delta, 0, 0, delta. But that's just 0, 0, 0, 0, isn't it? Okay, and so obviously this form doesn't produce an identity matrix because delta is 0. Okay, so this is just a 0 matrix. Okay, now what I'd like you to try to do is complete the proof on your own. Okay, try to complete the proof on your own. Now, what do you need to show? Well, you just need to show that yes, indeed, if delta is equal to 0, then this form doesn't give me an identity matrix. But is that enough to show that? I mean, that doesn't necessarily imply that an inverse doesn't exist, right? So what you need to show is that if delta equals 0, that implies that A is singular, right? So you have to. It's kind of a combination of proving that there's no other way for the matrix to be the identity matrix to be created from A and its inverse than this way. Okay, that would be one way to approach it. Right, but what we've shown is just that this form doesn't produce an identity matrix. This form of the inverse here does not produce the identity matrix if delta is equal to 0. Okay. Additionally, you couldn't divide by 0, so 1 over delta is not going to work out. 1 over 0 doesn't work. All right, so this is kind of undefined also. But see if you can complete the proof on your own. Okay. Excellent. Excellent. Okay. So this is the case for, this is the approach you want to use if your matrix is 2 by 2. What about other dimensions? What about other n by n matrices, n greater than 2? How do we find the identity matrix, or sorry, the inverse matrix for matrices with higher dimensions? Okay, well, it turns out that it's a little more challenging, but there's a definite approach to doing it, a definite way to do it. And so here's the general method. Okay, a general method. This also works for 2 by 2s, although you would never really want to use this if in the case of a 2 by 2 because it's not as quick, but you can test it on a few. So first thing you want to do is, I'll just give you kind of the itemized list and then we'll go through an example. So given A, we want to create a IN like this, augmented matrix. Okay, so you want to create an augmented matrix from your A and some identity matrix. Okay, so for example, maybe I'll have a running example as we talk these through. So let's say A is equal to 1, 2, 3, 4. All right, then what I want to do is I want to set up A identity as 1, 2, 3, 4, augmented with 1, 0, 0, 1 over here. Okay, so this is the A, and this is the identity. Okay, pretty straightforward. We're kind of used to augmented matrices by now, so this is sort of normal. So that's the first thing you want to do, is want to set that up. And then using row ops, using row operations, you know, and when I say row ops, I mean 1, 2, and 3, the row operations that we discussed previously. So using row operations, we want to put A, IN into reduced row echelon form, right? We want to basically row reduce this using Gauss-Jordan, and we want to find the reduced row echelon form of this augmented matrix. Okay. Now, here's where the identity starts to pop out. So if the left-hand side, okay, meaning this side, the 1, 2, 3, 4, upon doing these row operations and moving this into RREF, reduced row echelon form, if the left-hand side cannot be converted to IN, then the matrix is singular. The matrix A is singular. Right, so let's think about this for a second. Let's think about this in terms of our A here. So I start with 1, 2, 3, 4, and then I've got 1, 0, 0, 1, right? And my goal is to convert this into reduced row echelon form. Let's say I'm able to get it into this form: 1, 2, 0, 0, and something, 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 something. We don't know. So in this case, this is not the identity, right? That's what this item 3 is saying. If the left-hand side, this side here, cannot be converted to the identity, then the matrix is singular. Right? Another way to say that is if A has rank less than N, Right? So here the rank would be less than n. The rank is only 1. Right? And so in that case, the matrix A is singular, and this is just gobbledygook over here. It's not anything fancy. Now, if, however, otherwise, right? Otherwise, A is non-singular. A is non-singular, and the last n columns of A in is our inverse. Okay, so on the other hand, right, if you do this, if you start with 1, 2, 3, 4, and then 1, 0, 0, 1, and you reduce row, you do Gauss-Jordan elimination on this, or row reduction, and you get to this form, 1, 0, 0, 1, and then something, 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 something. If you can get it into this form, where this is equal to in, then this guy over here, this is the inverse. That's A inverse. Okay? That's how I mean, this works in general. Right? This is going to be, in general, the way to find the inverse of a matrix. You have to plug it into this augmented matrix form, put it into reduced row echelon form, and the inverse will just pop out. It'll just pop right out of there. Right? It jumps. This identity matrix over here becomes the inverse matrix. It's kind of remarkable, actually. Okay, and so what happens? I mean, you kind of think of it like this, high level. You start with this, right, and then you do row operations until when? Until you're in reduced row echelon form. And what you're left with is the identity and the inverse. Amazing. Right? So any matrix identity or any matrix inverse can be found using this procedure. Okay. Let's do an example. Let's try this example on the one we saw previously. So let's say m is equal to -5, 2, 9, -4. Now we know this has an inverse. We've actually calculated the inverse in a previous example. But let's do it this way instead. Okay, so let's set up min here like this. Right, so it's -5, 2, 9, -4, and then 1, 0, 0, 1. Okay. All right, let's go ahead and do the row operations here. And so this would be 1, -2/5, and then this will be -1/5, and 0. And then 9, -4, 0, and 1. Okay. And then we can multiply by 9 and bring that down. So I would have 1, -2/5, -1/5, 0. And then I'm going to get a 0 here, and then this is going to be 18/5 minus 4, and then this will be 9/5, and then that will be 1. So what is 18/5 minus 4? That's going to be 18 minus 20. So I'm going to rewrite this. 1, -2/5, -1/5, 0, and then 0, and then 18/5 minus 20/5 is -2/5. Then 9/5, and the 1. Okay. All right, and then I can multiply this bottom row by 2/5, right? And when I do that, I have 1, -2/5, -1/5, and 0. And then I got, so again, we're multiplying this by, 5 halves. My bad. Yep. 5 halves times that bottom row. And so I get 0, and then I have 5 halves times negative 2/5 is 1, and then 9 over 2, and then 5 over 2. Okay. And it's just a hop, skip here, and you'll see that this is 1, 0, 0, 1, and then you're going to have negative 2, negative 1, negative 9 halves, and negative 5 halves. Okay, let's see if we can get to that really quickly. Okay, and this is going to be the same answer as what we had previously. Okay. Perfect. Perfect. Okay. All right, let's move on here. Another theorem. So this one kind of follows from the general method that we just described, and I think I even said it as I was describing the method to you. But an n by n matrix, A is non-singular if and only if the rank of A is equal to n. Right? It has to be a full rank matrix in order for it to have an inverse. Okay. So how does this, I mean, we don't need it, we won't prove this, but like we can outline the proof, right? We can kind of give the reason. It follows from the previous process, doesn't it? Okay, it follows from the previous process. Namely, right, like if you have A augmented with in, this can only be reduced to in A inverse. This can only be reduced to that if A has n pivots. Right, it's got to have n pivots in order for it to be equivalent to I of n, right? This has n pivots. This must have n pivots. It only has n pivots if it has rank of n, right? And so in order for this process to produce an inverse, which is a general approach to producing an inverse, this matrix has to have full rank. Okay? And so if, another way to say that is, this augmented matrix cannot be converted into this form. If that's the case, you know, A won't be equal to in, and that'll be because the rank is less than n. So if A is not equivalent to I of n, it is because the rank of A is less than n. Okay, so if the rank of your matrix is less than n, then it's not going to have an inverse. Okay. All right. Very good. Very good. All right. Making a lot of progress here. Matrices are very interesting structures. I'm sure, you know, like if you think about this just in the most general sense, like we're literally just taking an array of numbers and spinning up incredible properties of just arrays of numbers. You know, just, you know, a random array of numbers has amazing properties. And that's kind of what we're up to right now, just looking into those amazing properties. Here's another one. Okay, let's let AX equal B represent a system. And let's let it be a system where the coefficient matrix A is square. So what does that mean? Well, it means that the number of equations is equal to the number of variables, right? If A is n by n, that means there are n equations and n variables, okay? So n equations and n variables. Okay, so let ax equal b represent a system where a is square. It's the coefficient matrix and it's square. Then two things. One, if a is non-singular, right? If a is a non-singular matrix, then the system has a unique solution. The system has a unique solution, and that solution is x equals a inverse times b. That's remarkable, right? Because this is basically saying to solve the system, you can use the inverse. If you know the inverse, a inverse, you can just multiply it by the scalar matrix, and it'll spit out the X matrix. Kind of remarkable. This is only in the case of square matrices, however. Okay. And the second item is if A is singular, right? Non-singular up top. If this is singular, if instead it's singular, then the system either has no solutions or an infinite number of solutions. Okay, no problem there. That seems to probably make sense too. So if you think about a singular matrix, we just talked about what the implications are to the rank. The rank is less than n in that case. Right, so if the rank is less than n, then that means when we row reduce, we're going to have independent variables, right? Or we're going to have an inconsistent equation. One of the equations might be inconsistent, like 0 equals 20 or something. That can happen, or you can have a row of all zeros, meaning you have an independent variable. So in those cases, we've seen previously that when you have independent variables in the system, then the solution is either not going to exist or it's going to be infinite. Okay. And so something that kind of follows, from this that is important is that ax equals b has a unique solution if and only if a is non-singular. Right? That's kind of, that has a certain sort of beauty to it, right? So a unique solution is kind of the most interesting case, like when there's just one solution, and that only happens for non-singular matrices. Right? In fact, it happens for all non-singular matrices. If A is non-singular, then ax equals b must have a unique solution. That's what this is basically saying. Okay, that's a very nice idea. Let's jump into a proof of this one. Okay. First, we'll go this direction. We'll let A be non-singular. Let A be non-singular. So what happens if A is non-singular? Well, let's start with the system here. Ax equals b. If A is non-singular, that means it has an inverse, right? And so that means I can multiply both sides by the inverse. Right? And obviously here I'm going to get the identity. Right, so you can kind of think of these two going together like that. And that's going to imply the result that x equals a inverse times b. Okay. And so something to notice here, right, with that a inverse times b, this is a inverse is n by n, b is n by 1. So a inverse b is n by 1, right? So something to notice, right? So this, x is n by 1, so a inverse b is naturally n by 1 as well. Now, is this a unique how do we know this is a unique solution? Well, it's kind of obvious, but let's make it really obvious. So assume y is a different solution. Right? Assume y is a different solution. So you have a different system. A times y equals b. Okay. Well, then I know that y is going to be equal to a inverse times b. But a inverse times b I just saw is equal to x. Right? So y is equal to x, isn't it? I mean, so there's no way this can produce distinct solutions. It has to be unique. Okay. All right, so that kind of shows item 1. Okay, so that sort of shows item 1. So if A is non-singular, then the system has a unique solution. That's what we've shown, and it has this form A inverse B. What about item 2? Well, let's assume that for item 2, A is singular. Let A be singular. What does that mean? Well, it means the rank of A is less than n. All right, it's not equal to n. And not all the columns of A will have a pivot. So not all the columns are going to have a pivot. So, I mean, two things can happen, right? You can have two options here. The first option is you're going to get a matrix like this. 1, 0, 0, 0, star. Something like this. Right? And this is going to be an inconsistent system. Right? Which means no solutions. Or the other thing that can happen when you have a rank A is less than n is that you can get something like this. 1, 0, 0, 0, 0. Right, I'm just taking a generic 2 by 2 matrix here, right? So something like you could get something like this. Now, what does this mean? Well, this means that this second variable is independent, and so in this case, you'll have infinitely many solutions. Okay, and this is just a consequence of the rank being less than n, meaning the pivots will be less than the variables. So some of the variables are going to be independent. Okay, and that's more or less how the second piece of it works, which is kind of what we described earlier. Okay, so we can kind of think of this as a proof. You can obviously write this up better, make it a little more concise, a little more rigorous, but this kind of shows you why it's true. Okay, excellent. Excellent, excellent. So that takes care of inverses. We'll end it here. Now, next time we get together, we are going to shift gears again and jump into determinants and eigenvalues. This is a very interesting and somewhat complicated section of linear algebra, but I find it to be very interesting. I mean, I think you will as well. Determinants and eigenvalues and eigenvectors and diagonalization. We're going to kind of jump into lots of different things. So until then, take care, and we'll see you all next time. Take care.